Welcome. In this little tutorial, I'm going to show you how to build a language in MPS. We'll build a little state machine language with events, variables, states, transitions, and guard conditions by reusing an existing expression language. We'll also build a second language that tests the original state machine language, and we can even run this to execute the tests. Finally, we conclude by illustrating how to build tabular notations and diagrams as part of the overall state machine story. All right, part 3. We should add transitions. So initially, that's of course the same story as before. Transition. Now, the transition obviously goes into a particular state. So there is a target, which is a state, exactly one. And it is also triggered by an event. So we could also add a second reference to the event that triggers it. But I'm not going to do this. Instead, I'm going to build the language in a more extensible way because transitions might be triggered by other things than events in the future. So I'm creating a trigger, which is abstract. So we'll see how we connect that to events in a moment. So the transition then has a trigger, which is a trigger 1. So now the editor for that thing can be defined as a horizontal list, of course, on, and then the trigger, go to the target. And now you notice that because we have made the target a reference, we can only select the reference syntax for the editor. Let me actually change this so it's less confusing. So we have two different arrows here. So what this means is of the target state, show the name to represent the reference. So that's good. What's missing, of course, is the event trigger, which is a trigger, and which in turn references the event 1. And how do you represent an event trigger? Well, of the triggered event, the name. All right, so let's see. Here's my traffic light. Oh, I can't yet put something into the state because I didn't add the transitions in the state. So transitions, transition many in the state, right? And then here we put another horizontal collection, whoops, indent, and the transitions once again configured vertically. Now we can add a transition. Now this directly gives me the target states as opposed to giving me the transition object into which I then insert the trigger. The reason is that I forgot to give this an alias. If I don't give it an alias, then the transition is a smart reference, a concept with exactly one target, and it behaves differently in the editor. So we can now create a new transition, and we can select the button, the event, and the target state, and maybe doing the same thing, going back to green. Now, you notice that this is wrong, right? Because it goes into itself. This might be okay, but let's say for our state machine, we prevent this. So we're going to add a type system checking rule for now, for a transition, and we say if t target equals t dot parent, which is the state in which we are cannot transition into self on the transition, and we'll, on the transition. So now we get both of them as an error, and of course I wanted to change this to green and this one to red. Now, just to drive home this notion of internal objects versus names, the fact that I use the name of the state here to represent the reference can be changed, right? I can change this to, instead of the name, doing it this way. Now it looks like that. It's not very useful, but the references still work and the code completion is still the correct thing. I only decided to represent the reference as these three X's. Again, not useful in this case, but it shows how the system works internally. It's based on unique IDs and not on names. All right, so what else should we do? Let's create a second state machine. Another one, and I give it an event. Dummy. I can see dummy. Why? Because I did not configure, I didn't define which, events are allowed in terms of targets for this reference. Similarly, I give this here a state S, and then I can of course see that S here as well. So that's why we have to define a scope. A scope is available under the constraints of the respective element. I'm referencing the or specifying the scope for the target reference. I use a reference scope. And basically, how do I find the targets for a reference? Well, from the context node, where is it? Here. I'm going up the tree until I find a state machine. And then I ask it for its contents. And then of these contents, I only want the states. So this is a list of state, right? You can, ask the tool. So this is a sequence of states, right? But it has to, I have to return a scope. So what I'm doing is I'm going to create a list scope, which I import from the MPS libraries. List scope. For named elements, and then I'm putting in these states. So rebuilding the language, going to my traffic light. Now I can only see these two. Similarly, for the event trigger, I go to its constraints. Creating for the event here, reference scope, context node. It's basically the same story, right? So I can just copy it from the from the transition constraints. I'm just going to copy this whole story here. And of course, instead of the states, I use the events. Compile. And now I can only see my own, B2. It's available. All right. So few more things are missing. I guess having two states of the same name works perfectly from a tool perspective, but it's not useful from a domain semantic perspective. So let's prevent this. Let's go to the state and do another checking rule where we would say if state parent state machine, I'm grabbing the machine, right? If the machine's contexts. Sorry, that's wrong. That is a state machine, right? The state's parent is the state machine. The contents of concept, and I'm grabbing everything that has a name, right? If its name, if any exists where the name equals my own state name and the thing is not me, then I have found another state with the same name. So, and that is an error, or another named thing with the same name. Duplicate name state. So I'm getting this twice because the check, of course, is run for both. You could consider this good or bad. It depends. You can also implement this check differently by going to the machine, iterating through all the named elements, putting the names into a set. And if when putting it into the set, the same name is already there, then you found the second occurrence of that same name. So you might prefer that. All right, but it works in principle. Now, one thing's still missing. We have to define one of the states as the initial state, the state in which the state machine is by default when it starts up. And so the way we do that is we're going to give the state a Boolean property initial. And we could do it by just putting this initial property here. And now it looks like this. It's kind of correct, but it's ugly, right? Not nice. We could change this here and include the bool language and then use a checkbox for the initial. And then it looks like that, which is kind of cute, but also not what you'd want for a textual language. So that's why we're going back once more. And we're including the grammar cells language. That's a language that helps you build nice behaving editors for textual notations. And we're making this a flag. And now it looks like this. It has this flag here. You can just type initial, right? Removes it again. So if the Boolean flag is true, the flag is shown, otherwise it isn't. So that's exactly what you want. And then the final thing we need to do is we want to make sure that the state machine has exactly one initial state. So we're going to do the following. We're going to create a behavior method. First, we're going to create sequence node state, right? So that is states. It returns this contents of concept state. And then we do another one of these, which is the initial state, which is the states find first where it is initial, right? So that's good. And now we need the checking rule here. We can put something else here. We can say of the state machine, we grab the states, right? And then we select those where initial would be marked as initial, and if marked as initial dot size is not 1, then we output the error exactly 1 initial state required for the state machine. Compile, and if we remove this, we get the error. If we add this back, copy it, we get this error exactly as it should be. All right, so this brings us to basically the fourth commit. Constraints for name uniqueness as a single initial state. no self transitions, and the internal structures for events, transitions, and their editors. So we have arrived at this commit, commit number 4. We'll continue with the testing language in the next video. But just to briefly recap, we've created a state machine which has a bunch of contents, and the contents are either, we can actually look this up. So the contents, we can look at this in the hierarchy. We can see there is events and states. There's also the empty thing, which we, yeah, it is there. So while we're here, right, so we don't want to be able to actually create an empty thing this way. We can do this by creating in the editor, a default substitution menu. Substitution is what happens when you do code completion, and the default substitution menu is used by default. And by defining this empty, by not putting stuff here, it basically prevents you from entering something, in this case the empty state machine content, by code completion. Now it's gone, right? Notice also that you can start typing initial, right? And it makes it an initial state. So this flag cell here allows you to start typing the state with the flag text. Anyway, so we have got states, we have events, we have constraints that check that we have exactly one initial state, that the state machine must start with an uppercase name, and we have a check for the state, which verifies that there is no other state with the same name, and we check that the transition does not transition into itself. We have created scopes where we find the allowed targets for the state machine, which is the surrounding machine's states, and the events would be the surrounding machine's events. All right, so that's a very simple language. More in the next video.